Hello and welcome to a new video. Exercise 14. Small objects are released from rest at A and slide down the smooth circular surface of radius R to a conveyor B. So we have objects that are released from rest at A. So V at point A is equal to 0. These objects will slide down this smooth circular surface. When we say a smooth surface, this means that we don't have any friction force. The circular surface has a radius capital R as seen. So A, let's say O, is equal to the distance R is the radius, and OB is also equal to the radius. So these objects will arrive at point B where we have a conveyor belt. So we have like a tapis roulant where the objects will continue horizontally. Okay, so a conveyor means that you have this system. Question A, determine the normal contact force N between the guide and each object in terms of theta. So we have to find what is the normal reaction. What is N? First, let's note that we have part of a circular motion. So we can use the normal and tangential components of the acceleration. And to find the normal reaction, we have to apply the fundamental relation of dynamics. So they asked about a force. The main equation dealing with forces is the fundamental relation of dynamics, or Newton's second law. So let's take our system as the object that is released from A and going to B, and apply the fundamental relation of dynamics. Sum of the external forces equal ma. Now, since we want to find what is the normal reaction, and we know that the normal reaction is directed to the center of the circle, so here we have the normal unit vector. The normal reaction has the same direction as the normal unit vector here, noted as En, or simply N. So let's project the fundamental relation of dynamics on the normal reaction to find the expression of N. Okay, so we have mg plus N equal ma. Now, what is the projection of mg along the normal unit vector? So in the figure, they said that theta is the angle between OA, so this point is point O. Theta is the angle between OA and the position vector R, so OM, for example. So this is angle theta. Now, what is the projection of mg along En? It's equal to minus mg cosine of this angle. We need now to find this angle. Now, if we draw the line which is parallel to OB and passing through M, so if we draw this line, we can notice that this angle in red is equal to this angle in red. Let's say it's the angle alpha, where alpha is the complementary angle to theta. So theta plus alpha is equal to 90 degrees. So this is also the angle alpha. This red angle is equal to this red angle, corresponding angles, and alpha plus theta is equal to 90 degrees. So this means that the projection of mg along the normal unit vector will give us, so this is the normal unit vector, En. It will give us minus mg cosine alpha it's equal to minus mg sine of theta. Now we need to project the normal reaction vector on the normal unit vector, it's plus n, equal m times the normal acceleration, where the normal acceleration is equal to v squared over r. We need to find what is the normal reaction. So n is equal to m v squared over r plus mg sine theta. So mg and sine theta are well known. The radius is also known, but we don't know what is the speed of the mass at any point on this circular surface. So we need to find what is v. Let's now project the expression of Newton's second law on the tangential unit vector. So let's draw what is the tangential unit vector. So here we have the tangential unit vector denoted as ET or E tau. It's the same. So we need to project the vectors mg and n now on ET. So mg on ET will give plus mg cosine theta. Now the projection of the normal reaction on ET is 0 because n is perpendicular to the tangential unit vector, and the acceleration along t is equal to at, so we will have mg cosine theta is equal to mat. We can simplify with m to find that a is equal to g cosine theta. And here there's a very important remark, that the acceleration, the tangential acceleration, depends on theta. The tangential acceleration is not a constant. It doesn't depend on time directly. It depends on theta. So a is a of theta. This means that let's use the expression v dv equal at ds, okay, where ds is equal to r d theta, and r is simply the radius of the circular surface. It's a constant, so small r is equal to capital R, the radius of the circle. Now let's find v. So we will write that v dv is equal to at ds, where at is equal to g cosine theta, so g cosine theta, and ds is equal to r d theta. We can notice that here the variables are well separated, so v is with dv and cosine theta is directly with d theta. So this means that we can immediately integrate. So integral of v dv between 0 and v is equal to rg cosine theta d theta between 0 and theta. So theta 0 is clear to be equal to 0, and the final theta, the final angle of rotation, is theta. So integral of v dv between 0 and v will give v squared over 2, and the integral of cosine theta d theta between 0 and theta will give sine theta between 0 and theta, with sine 0 equal to 0. So the expression of v squared will be equal to 2rg sine theta. We need to have v squared, in fact, to put it in expression 1, the normal reaction. So n will be equal to m times v squared over r, where v squared is equal to 2rg sine theta, plus, so n is equal to this quantity, plus mg sine theta. So we have a common factor mg sine theta times 1 plus 2. So this will give us n equal 3 mg sine theta. Now question B. Specify the correct angular velocity omega of the conveyor pulley of radius small r to prevent any sliding on the belt as the objects transfer to the conveyor. So, once the object arrives at point B, it will go on a conveyor belt, and it will have the new speed of the conveyor belt. But there is a critical point B where the objects will may experience a change in their speed, because on the circular smooth surface the speed was v equal radical of 2rg sine theta, and now the speed of the conveyor belt is equal to r omega. So the mass can experience a change in speed, and maybe there will be a certain sliding on the belt due to this change in speed. So the question is, what is the particular value of omega to prevent any sliding on the belt? What is the angular velocity omega in order for the objects to transfer easily on the conveyor belt without experiencing any change in their speed? So, in other words, we should have a rotation with no slipping in order to prevent any sliding. So at the particular point B where the angle theta is equal to 90 degrees, the objects should continue with the same speed. So the speed of the belt here should be equal to the speed of the objects on the circular smooth surface. So at angle theta equal 90 degrees, so at point B, the speed of the belt should be equal to the speed of the object. So we will write that V belt is equal to R omega is equal to the speed of the object found from the circular surface, and this is equal to radical of 2rg sine theta. So we have to write R omega is equal to radical of 2rg sine theta, where theta is equal to 90. So r omega is equal to radical of 2 capital R times g, and finally we can obtain the value of the particular angular velocity necessary to prevent any sliding on the belt, and this is equal to radical of 2 capital R g over small r. So this exercise is a classical exercise dealing with the application of Newton's second law with the use of the normal and tangential unit vectors. We also used the expression VdV is equal to AT ds, because we noticed that the acceleration or the tangential acceleration depends on theta.